In the last class, we learned how to use scipy for solving a set of differential equations. Now we will consider a couple of applications where we can use that knowledge. So let us take a very simple case of, say, projectile motion. That means motion in two dimensions. Say this is x and y, and suppose we have a body here and just send it with a velocity vx, and initial position here is say x0 y0. Then we have say gravity in this direction, that is the acceleration. So we expect it to go something like this. So let us try to calculate this trajectory. It's a again an initial value problem. X and y are known at t is equal to 0, and also vx and vy are known, and the acceleration in the vertical direction is known, and acceleration in the horizontal direction is 0. So putting this information together, let us try to write a small program. Say first we have to import numpy and matplotlib with this statement. Then from scipy we import the integrate module. Integrate. Now the ax is equal to 0, that we know, and ay is equal to minus 9.8. That gravity is in the negative y direction. So now the function, the derivative has to be defined, and it will be a function of say position and velocity. So let's call it as a variable name pv, and the second argument is required for the solver, so we'll put it here. And what this pv contains, pv is an array of two variables. pv of 0 is x, and we have pv of 1 is equal to y. So then we will have pv of 2, the third one is vx, and pv of 3 is vy. So every time this function is called, this pv will contain this information. So accordingly it should return the derivative of each element, and we know that is x, the derivative is vx, that is pv of 2, and then vy, right, pv of 3, then we should return ax and ay, because that is the derivative of vx and vy. So every element, the corresponding derivative is returned. Now the time, let us make a array going from 0 to say something like say 5 seconds, and put a step size of 0.01, and now we can put the initial conditions. So let us call it as pv0. Let us put it inside an array, say 0 and 10, that is the x and y coordinate, and vx let us put say 20, and there is no vy, vy is 0. Now we just say pv is equal to integrate dot ode int, that is the function name from that integrate module, and this is our function, and this is our initial conditions, and this time. Now what is left is plot. We want to plot x versus y, that is extract the column, again the same, first column, that is the x coordinate, and the second column is the y coordinate, and save this as something like say 2d.py. Now let's open a terminal, and say python 2d.py. So you can see here this is the plot x versus y. So this is the projectile thing. So let us make a change, so that instead of putting it in this this direction, let us put it in this direction initial. So give a vertical component of the initial velocity. Say here initial velocity, let us make it, say that also 20. That means we are just putting it in this direction, I mean something like 45 degree, right? So save that, and so now you see that it is from this x is equal 0, y is equal to 10. From here it goes with the velocity component vx and vy, both are 20, and this is the path it is taking. So now if you want, you can plot any of these parameters against time and see how things change. So this is one example. Probably we can just go into another problem which is slightly, I would say, simpler than this. That is our that mass and spring problem, that we already done it using Euler method. So say k is equal to spring constant and m is equal to 1, say. And here the problem is you have a fixed a spring, one end fixed and other end you have the mass which can move frictionless, slide frictionless. And if you stretch the string by, say, by an amount, say x or something, if you release it, it will keep on undergoing oscillations, right? So we want to find out the graph time versus x and vx. So mass and what will be the derivative here? So here the position and velocity, only one component is there, right? X, and PV of 1 will be Vx. So there is no, it's a one-dimensional problem. So what we have to return here, X is Vx, and here what we should return, you should return Ax by M. No, Ax, you have to return Ax, but Ax is what? And in this case we know that in this mass and spring problem the force is equal to minus kx. And what is acceleration? Acceleration is force by mass. So we have to put that here, F, so that is force by mass is minus k say k by m into x. X is equal to PV of 0, right? That is appearing in that as a first element. So now again this is done initial conditions. Say we stretch it initially by 2 units, initial velocity is 0. So initial x is 2 and initial velocity is 0. And now we have to plot not x versus y. X versus y also will give you a sort of ellipse, but we want how it changes with time. So we'll plot both position and velocity as a function of time, like this. So, and file save as, say it's a mass spring problem, ms dot py. Let us see what happens now running it. So you can see this is the result, and what are we be seeing here? We are seeing here, first one is our position. You can see from here at t is equal to 0, position is at 2, right, and velocity is 0. And when you release it, by the time the position reaches 0, the velocity has reached somewhere like 6. So this goes on oscillating like this. So it's, you can see without solving the equation or just by numerically solving the equation, we can see it is a sinusoidal oscillation. And now probably we can take another slightly more complex problem, like movement of a charged particle in a electric and magnetic field. So coming to this problem, that means we have a charged particle. So let us define the mass and charge of that. Put some arbitrary number, say charge is equal to 5. You can use any number, or you can use both of them are as 1. So now Ex, the electric field, X component, then Y component and Z component, we are keeping all of them as 0. Then Bx 0 and By is also 0, and Bz let us give some value. So this is our magnetic field, and what will be the derivative? So it's all decided by the Lorentz equation. And what is the Lorentz equation? Force acting on a charged particle in an electric plus magnetic field is charge into E plus V cross B, the cross product, right? This is the equation. So you have to write the expression for V cross B, and let us do it in this 3 separate coordinates. So that means PV will have 6 elements, position, velocity, because 3 coordinate X, Y and Z. PV 0 is equal to X, and then Y, Z, and 3 will be Vx, right? So here PV of 1 will be Y and 2 will be Z. Then Vx, Vy, Z, so Vz. So we will have 6 of them total, and here we have to return like Vx, Vy, that is the derivative of X and Vz, and here acceleration, right? Acceleration should be returned Ay and Az, because function is supposed to return the derivative of each element in this array that is coming. Now we have to calculate this. So but Vx we don't have to calculate, because Vx we know already it is PV of 3, right? So that is how it is right from the beginning. And Vy and Vz will be PV4 and 5. How about Ax? Ax is equal to Fx by m, right? The force. So you have to calculate Fx. Fx is equal to Q into Ex plus, now the V cross B. V cross B, the Vx will be given by Vy into Bz. So this goes cyclically, that is the definition of our say Vz into By. So this all you have to do is look at the definition of the cross product, and this force divided by mass. This is the x acceleration, and now so it's divided by mass acceleration in the x direction. Now we have to get our editor is giving some trouble, it looks like. So let us type what will be Ay. Ay is equal to Q into let us save these and restart the editor once. There is something not quite alright with the editor, so we will open ms dot py. Let's see whether it solves or not. Now Ax and Ay and Az. So Ax, Ay will be Ey, and here what will be thing. Again we have to see this here y and z, so here it will be x and z should be there, right? Z vx bz and vz bx, and here az this will become z, and here it will be vx by, and the sign also one has to see here, plus actually one could change the position here. This vx bz could be put on the left side, and here now the last one vz that will become vy bx. So let us save this. So this is our derivative. So you calculate the force, and force by mass is the acceleration, that is the velocity is derivative, time derivative. Now time array is given here, say suppose do it for 50 seconds, and how about the initial condition? So initial xyz, let us take it as 0, and initial velocity, say we give only in the x direction, y direction there is nothing, z direction also there is no. So now the output we can, let us run this, v cross b. Oh, here this line should have been commented, right? Oh. Save ay. So here there is a parenthesis mismatch, because here 1 2, so that's the error, but something went wrong. We have q not defined. Oh, this, there is a typing mistake, charge q, so that's why we got error. Now run it again. So this is how it shows, but this is the time evolution of x and y components. What we need is the trajectory, that means we have to plot x versus y. Let us do that. X versus y. And you see you get a circle. That is what is expected, right? And the circle is having a diameter of 2, right? This is minus 1 2. Now you can try something like, say, change the bz. Suppose you, instead of 5 you make it 10 units. So what should happen now? You can see the diameter has now become 1. Instead of, it has become a smaller circle, right? A bigger force, and it is coming into tighter and circles. And if you increase this velocity, what will happen? The initial condition, if you give a, instead of this you give 4, say, then you will find it will go into a bigger circle, right? A diameter of 4 now. So this, all these things explore, but now the thing is this 2D plot won't help. At the moment you give some ez, this graph will become 3-dimensional. So we should be able to plot a 3-dimensional graph. So let us try to do that. Instead of this plot, 2-dimensional plot, we should do a 3-dimensional plot, and that can be done by some simple commands. I'll just do a cut and paste so we can save some typing. So here what we are doing is, from this MPL toolkits, that matplotlib toolkits, mplot 3D module you import. Now from that you get the access 3D is imported, function access 3D, and then you create, say, some variable ax is equal to access 3D of figure, and then you are giving this pv1 pv2 pv3, that means xyz coordinates. So let us save this and try plotting it. So you can see the same plot, but it is in the 3-dimensional. You can see it is z plane. So if you want to mark the label, you can do that. So let us say at least mark the z-axis, right? Set z label so that we can easily find out, okay, this is z-axis, but it is in the totally in the xy plane, right? Z is equal to 0. Now we'll give an electric field in this direction. Small component Ez will provide. So Ez, let us make it say 0.1 unit. Save, and then you see immediately it is just going up in a helical path. And it becomes interesting if you give say Ey, you give something, say some value, slightly higher value, and so it is something totally different. Probably what we can do is we'll remove that Z portion and give this alone. You'll find it is tracing a cycloidal path now, like this, instead of the helical path, and it will be clear if you give a slightly bigger Ey and no Ez. So that really work. Ey, oh no, sorry, Ey should be say 1. What we have to change is Ey, yes, Vx Ey, okay, Vy we are giving, so instead of Ey let us give Ex. So you'll find it is tracing a path like this, and now let us increase this further. This, you have to see that we are giving the initial velocity in the x, and we have given this electric field also in the same direction, and you can see this is a sort of cycloidal path it is taking. It goes like this. Anyway, now you can change all the initial conditions. Probably you can put other components of the magnetic field. Say if you just put off this electric field and give only a small Z, and Bz, if you give a By also, you can see what happens, what kind of trajectory it is tracing. So one can do all this exercise and try to interpret the results. But the thing what you have to see is, now this code has become slightly bigger, 30 lines. So do we really have to do it in 3 components? Like this is our equation, why not do it in the vector form? And NumPy allows us to handle the vectors. So if I do something like this, say instead of specifying all these components, I simply say array of the list inside this, so a 3 and list. So this becomes my electric field, and this is my magnetic field in the vector form. And the reason is all this cross product and all this NumPy will understand. So now we will come here, and Vx, instead of that we are going to define a V, that is again array of, say inside the list we have to put PV was 3, 4 and 5, right? Vx, Vy, Vz. So you have all the velocity components, only one V. Now instead of acceleration, x, all those things, we say A is equal to F is equal to QV cross B, right? So Q by M, let us put that first, into cross product, right? V and B. Alright. So Vx, Vy, Vz. Now we have to do here, we have to change, it is V of 0, V of 1 and V of 2. This again is a vector form, A of 0, A of 1, A of 2, right? So that's thing. we have given already. So let us see whether it works or not. Invalid syntax. So here array, okay, here there is a parenthesis missing, right? Save. So you see here the output is here already, and our code has become smaller if you just remove all these commands and everything. So we are around some 20 lines of code, and now we can come here and say electric field, put a z, save and run it. Oh, we have not got anything. Why? Yes, there is a mistake. We have forgotten to put our e plus. We are putting only v cross b, right? And what is required is e plus v cross b. So that was a mistake. That's why our electric field did not have any effect. So that was a mistake. You see that it is coming. So these are some of the simple things we can do with scipy, numpy and this Python language. So let us finish it here.